Hi guys, in our last video we looked at just the operation of a vector dot product here, just as an operation, how we do it and what it represents. But basically what we're going to start to get into is just applying the dot product, and so that means that we're going to have to evaluate expressions involving dot products. And one thing we want to be good with is just this idea of being able to come up with a value for a vector expression and know whether or not you're going to get a scalar as an answer or a vector as an answer. And so we're going to take a look at these examples here where we're given these three vectors u, v, and w, and what we're going to be asked to do is find the indicated quantity, but also kind of foreshadow a little bit, hey, you know, would my answer, would it be a vector or would it be a scalar? And so really quickly here, let's go ahead and throw something out there. When we talk about evaluating expressions, one thing that is always kind of around is this idea of PEMDAS. And so some notes that I do want to take on this are we still follow this idea of PEMDAS, but in terms of parentheses, this definitely still happens. And so we definitely want to look at parentheses as much as possible. And we're going to do what's inside parentheses first. In terms of exponents, I am going to write exponents here, but what I'm going to write is also usually only on only on magnitudes. And that is to say, a magnitude is a scalar, and we can often take scalars times themselves, but we don't ever multiply vectors. Okay, so in terms of multiplying vectors, it's just not going to happen, so we'll never raise to an exponent a vector. However, in terms of multiplication, there are two types of multiplication I do want to list here. We're going to scalar multiply, and that does take the same precedence as regular multiplication with real numbers. But we're also going to look at this as dot products. So dot products, when you talk about a dot product, it is not a product per se, but we still do it as importantly as we do products. Okay. So now division doesn't happen, and in terms of addition and subtraction, we definitely do addition. And in terms of subtraction, we just interpret this as add the opposite. And so we're going to go in this order when we evaluate some of these today. And so let's take a look at 15 really quickly here first. It says, you know, if we have a vector u, take u and a dot product with itself. So in terms of this here, we're just going to start with u dot u. And I actually think that it is entirely appropriate to rewrite it into component form and say, well, we're taking component form 3 times, or sorry, in a dot product with itself. So u dot u gives us this, multiply our horizontal components 3 times 3, and then we're going to multiply our vertical components another 3 times 3 as a matter of fact in this case. So what we get is 3 squared plus 3 squared, or 9 plus 9. We really get 18. And so part of this was evaluate it, but also part of this was to indicate whether we got a scalar or a vector for an answer. So in this case, we definitely get a scalar for an answer. And certainly that's something we could have told ourselves before we even started. Anytime you do a dot product of two vectors, you get a scalar for an answer here. And so I'm going to hop around a little bit here. Something more along the lines of, say, like a number 18 here. And so with v dot u, let me try to rewrite this again here, v dot u, and we're going to multiply that by w. One thing that I want to do before I kind of start on this is kind of foreshadow a little bit, what am I going to get here? Now in terms of order of operations, we definitely are going to start inside these parentheses, which means we're going to do the dot product first. And what do you know about a dot product? Well, a dot product yields a scalar as a result. So what we're going to get here is a scalar. I'm going to write that on top. Inside the parentheses, imagine now you take a scalar times a vector. What do you get for an answer? You actually get a vector for an answer. So knowing that this is what we're dealing with here, I'm going to go ahead and replace v and w in their component forms with negative 4 comma 2 in a dot product with, and w is 3 comma negative 1. And so we're going to go ahead and do those first, and then we're going to multiply that by the vector w, which w is also 3 negative 1 over here. And so v dot u, actually, let me take this back. I must have looked at this wrong. V is negative 4, 2, but dot u, beg your pardon, is 3, 3. And then we're going to take that times w, which is 3, negative 1. And so go ahead and let's do our dot product first. But we would get negative 4 times 3, that, plus now 2 times 3. There's our dot product. We're going to multiply that scalar times 3, negative 1. And so what we get in here really is this, sorry, negative 12 plus 6 times 3, negative 1, which is really negative 6 times 3, negative 1, which finally when we scale it, we get negative 18, but we get a positive 6. So I'm going to throw a box around this, and we're going to indicate that we clearly got a vector. So going forward, when we evaluate, I guess, a vector expression, just keep in mind that we go through the order of operations, and that when you dot product, you're going to get a scalar, but a scalar with a vector always gives us a vector. Cheers.